Hello everyone, my name is Han Dong-hyun, and I'm a PhD candidate in the IIXL lab. Today, I will be presenting the paper titled Self-Composing Policies for Scalable Continual Reinforcement Learning, which was presented at ICML 2024. Intelligent agents we aim to build must adapt to ever-changing environments, much like the real world. Continual Reinforcement Learning, or CRL, addresses this challenge. CRL focuses on agent learning a sequence of tasks over time, with the key goals of retaining past knowledge, which means avoiding forgetting and effectively acquiring new knowledge. However, traditional deep learning models suffer significantly from catastrophic forgetting, where performance on previously learned tasks drastically degrades when new tasks are introduced. The ideal CRL agent should be able to learn, adapt, reuse, and transfer knowledge seamlessly. To address catastrophic forgetting, growing network approaches emerged. The idea was to add new network modules for new tasks while freezing the parameters of old modules, thus preventing forgetting. A prime example is progressive neural networks, or PNN. PNN works by having each layer in a new column for a new task receive direct lateral connections from the corresponding layers of all previously learned columns. Each of these connections introduces new learnable adapter parameters. It's like continuously adding new information pathways and nodes laterally to each layer. While this method effectively prevented forgetting and enabled knowledge transfer, it suffers from a critical issue: quadratic parameter growth. As the number of tasks increases, the number of required connections explodes, leading to the total number of parameters growing quadratically, with the number of tasks severely limiting scalability. So, this paper asks a new question: how can you avoid forgetting, maintain linear parameter growth, and effectively reuse past knowledge? The core approach of component proposed in this paper has two parts. First, instead of connecting to all internal hidden layers of prior module like PNN, component utilize only the final policy outputs of previous modules. This alone significantly reduces the complexity of parameter connections. Second, instead of having a separate composer network, each module is designed to self-compose by selecting and combining prior policies based on the current situation, using an attention mechanism. This means it dynamically determines which prior policies are most relevant for the current state. The core of component is the self-composing policy module added for each new task. This module takes the encoded current state and the policy outputs from all prior modules as input. The first component is the output attention head. Its goal is to propose a tentative action VOUT by finding the best combination of prior policies for the current situation. It uses a standard attention mechanism where the current state acts as a query, and the outputs of prior policies serve as keys and values. The result, VOUT, is a weighted sum of these prior policies, with weights dynamically determined by the current state. It's like saying, given the current state, a mix of 30% of policy A and 70% of policy B seems like a good idea. Next, the input attention head extracts relevant contextual information from both the prior policy output and the VOut proposed by the output attention head to help the internal policy make better decisions. Finally, we have the internal policy, which can be a simple MLP. This internal policy decides whether to use VOut as is, refine it, or generate a completely new action. The module's final policy is the sum of this VOut and the output of the internal policy. This structure provides flexibility. If the combination of prior policies VOut is highly suitable for the current task, the internal policy can output near zero values, effectively reusing VOut. Conversely, if VOut is inefficient, the internal policy can actively learn new behaviors to solve the current task. The most significant advantage of component is its linear parameter scalability. PNN required adding new adapter parameters to each layer of all prior tasks for every new task, resulting in quadratic parameter growth. In contrast, when component encounters a new task, it adds only one new module of a fixed size, comprising attention heads as an internal policy. This is because it only references the final output of prior modules, not their internal structures. Consequently, component's total number of parameters increases linearly with the number of tasks, or ON. This maximizes memory efficiency, enables learning many more tasks sequentially, and also maintains relatively efficient inference times. To verify if component verify if component is effective, various experiments were conducted. It was tested on environments like MetaWorld for robotic manipulation and visual-based Atari games from the arcade learning environment. Key evaluation matrices include average performance to assess overall learning capability, forward transfer to measure how quickly new tasks are learned, and reference transfer to compare against fine-tuning from the best single prior task. Component was compared against several baselines and prior methods, including learning from scratch, simple fine-tuning, progressive net, which is PNN, and PECnet. To summarize the experimental results, component consistently demonstrated superior performance and forward transfer compared to other methods and simple fine-tuning RT across all tested environments. Notably, in the interference-heavy MetaWorld, component was the only method to achieve positive forward transfer, proving its robustness. In terms of scalability, component's parameter count increased linearly, while PNS grew quadratically. Inference time was also significantly more efficient for component compared to PNN as the number of tasks increased. Architectural validation experiments further confirmed that component behaves as intended, effectively reusing prior policies, learning new ones when necessary, and minimizing interference from irrelevant past knowledge. In conclusion, this paper proposed component, a scalable and efficient architecture for continual reinforcement learning. Through its attention-based self-competition mechanism, component successfully catastrophe forgetting prevention, effective knowledge transfer, and plasticity for new learning. This is believed to be a broad contribution towards developing realistic CRL agent capable of learning a large number of sequential tasks. Of course, challenges remain. Future work could focus on further optimizing computational cost for extremely long task sequences, enabling agent to automatically detect task boundaries and identifiers which are currently assumed to be given, and generalizing to more complex and diverse types of tasks. This concludes my presentation. Thank you for your attention, and I'd be happy to answer any questions you may have. Thank you.